Hello and welcome to this EE228 video. Today we're going to cover the introduction to Chapter 5 in Navi's book, which is Differential Equations. This lecture assumes that you have taken a class in differential equations, probably from the math department. We're not going to go through a lot of the background, but I do want to act as a refresher to what's already in your brains. So before we get into that, I want to remind you that we have talked about multiple ways of representing LTI systems so far. There was the operator notation, where the system is represented as a function that acts on a function, or an operator. And this was every system you can think of will take an input and give you the output. And this, whatever the S operator is, that is a description of what the system is. Another way to think about systems is via their impulse response. And this was the revelation that we can convolve any input signal with the system's impulse response, h of t, to calculate the output. And so this was, you might say, well, if we've already got the operator notation, why would we need another way to do it? Well, my point that I'd like to make is that it is much easier to find a system's impulse response than it is to find a system's closed form operation. That is, we can not create an impulse in real life, but we can create things that are awfully close to them. And in the lab, you can hit this black box with your approximate impulse, and you can get out an approximate impulse response. That you can then use to convolve with any other input you like to get the output due to that input. And that is a far cry from testing every possible conceivable input and observing the output and trying to discern some or divine some relationship between x and y to give you the S. Okay, so today we're going to address a third way to look at systems, and that's describing them as a linear, constant coefficient differential equation. And I forgot ordinary goes in there too. So sometimes, or if you're looking for a Google term to search, this occasionally goes under the acronym linear constant coefficient ODE, or ordinary differential equation. So this is the idea that for an LTI system, the output and its derivatives will be linear function of the input and its derivatives. So how does that look? You can think about the most general lin code as being the nth derivative of the output plus scaled versions of all the lower derivatives all the way down to, say, a1 times the first derivative and a naught times the 0th derivative, or the output itself. And we can set that equal to a linear combination of an arbitrary number of derivatives of a forcing function. So let's scale each one by a scaling factor, and we'll take the ith derivative of the input, dt to the I, and we'll let I run from 1 to m. In general, you can have n derivatives on the left and m derivatives on the right. Typically, physical systems are those that have n higher than m, but that's not particularly important for our discussion right now. So this is the most general form of a linear constant coefficient ordinary differential equation. It's linear because we are looking at derivatives of y and derivatives of x, and we're looking at linear combinations of those. Right? We're not looking at dy dt times y. That would be a nonlinear operation on the derivative and its functions. Constant coefficients, that just means that the a's and the b's do not change either with x, they do not change with y, and they do not change with respect to time. And it's an ordinary differential equation because we've just got derivatives with respect to time. There's no multivariable going on here. There's no partial derivatives. Okay? So this general form actually allows us to talk about the multiple parts of a differential equation. So when we look at just this, what's drawn on the left here, this is called the homogeneous part of the diffie-q. Right, and this is just the derivatives of the output. And on the right-hand side, we've got what's called the non-homogeneous part, And I will also refer to this as the forcing function. And this is because of my background in mechanical engineering, where you're talking about a physical force acting on a system. So that's where the idea of forcing function comes from. We will often just refer to it as the input and its derivatives. Input and derivatives. Because we're just going to take a broader perspective on this as a system rather than a mechanical or an electrical system. Now there's three parts to any differential equation. There's the homogeneous part, there's the forcing function part, and in order to truly solve this diff EQ, we also need what are called initial conditions. In other courses, these might be called boundary conditions, where if your independent variable is, say, space rather than time, then we'd need to solve a diff EQ where like position is 0 or position is 1 meter away. But all our systems will have its independent variable to be time, so I'm just going to call them initial conditions. And these are the n conditions that your output must satisfy. So for an nth order, little n, for an nth order diff EQ, you need n initial conditions. So, and they're typically listed from the lowest derivative up to the highest. So that means you'd have y of 0 is something, y prime of 0, the first derivative of y, has an initial condition, and this goes all the way up to the n minus 1th derivative evaluated at t equals 0 would be some constant, right? These are constants on the right. Yep, so there are n, what we call ICs, initial conditions. Okay, so to bring this home, to kind of get rid of all this generality with the n's and the m's and the a's, I think it's instructive to look at a system that you're very familiar with as electrical engineers, and that is everyone's favorite RC filter. So let's say we've got a voltage source over here whose voltage is given by the function x of t. Now this will be the input to the system, also known as the forcing function. That voltage will drive the current around this circuit according to a certain differential equation. And we're going to consider the output to be the voltage across the cap, the node voltage at this node. Okay, so to help derive what the diff EQ that describes the system is, it's instructive to start with Kerkoff's voltage law, which if we start at this node and work our way clockwise, we ascend x volts, we descend the current times the resistance, if we define our mesh current in this orientation. Right, that's the voltage drop across the resistor, and we drop the y volts across the capacitor, and that brings us back to our ground node. So this is almost a diff EQ, right? This has got a forcing function, and it's got output, and it's a linear combination of those, but it's not quite done because we have this third function that's neither x nor y. So to get rid of current, we need to remember the current voltage relation for a capacitor, which says that the current into a capacitor is proportional to the change in voltage across that capacitor. So there's only one current, so this capacitor current is the current, and so it'll get subbed into here. So that means that our x of t minus r times c times the derivative of y, and this might be a new notation for some of you, by a single dot above a time function, this means dy dt. Okay, think of it like a prime. And then we have our old y of t from before. Right, this is because there's only one current, so the capacitor current is the current, and Vc we're calling y of t. Okay, so to rearrange this to make it look like our classic general Lin code equation, I'm just going to divide everything by RC and move the y's to the other side as the x. So I get y dot plus 1 over RC y of t equals 1 over RC x of t. Okay, so in this case, A1 would be 1, A0 would be 1 over RC, and here we have B0 is also 1 over RC. All right, so here we've gotten this RC circuit into the form of a generalized linear constant coefficient ordinary differential equation. And we'll look at how to solve those in the next video. Thank you.